Section 4. You will hear a woman talking to a group of first-year science undergraduates about the developing science of nanotechnology. First, you have some time to look at questions 31 to 40. Now listen carefully and answer questions 31 to 40.
Today we're going to look at an important area of science, namely nanotechnology. So, what is it? Nano means tiny, so it's science and engineering on the scale of atoms and molecules. The idea is that by controlling and rearranging atoms, you can literally create anything. However, as we'll see, the science of the small has some big implications, affecting us in many ways. There's no doubt that nanotechnology promises so much for civilization. However, all new technologies have their teething problems. And with nanotechnology, society often gets the wrong idea about its capabilities. Numerous science fiction books and movies have raised people's fears about nanotechnology, with scenarios such as inserting little nanorobots into your body that monitor everything you do without you realizing it, or self-replicating nanorobots that eventually take over the world. So, how do we safeguard such a potentially powerful technology? Some scientists recommend that nanoparticles be treated as new chemicals, with separate safety tests and clear labelling. They believe that greater care should also be taken with nanoparticles in laboratories and factories. Others have called for a withdrawal of new nanoproducts, such as cosmetics, and a temporary halt to many kinds of nanotech research. But as far as I'm concerned, there's a need to plough ahead with the discoveries and applications of nanotechnology. I really believe that most scientists would welcome a way to guard against unethical uses of such technology. We can't go around thinking that all innovation is bad, all advancement is bad. As with the debate about any new technology, it is how you use it that's important. So, let's look at some of its possible uses. Thanks to nanotechnology, there could be a major breakthrough in the field of transportation, with the production of more durable metals. These could be virtually unbreakable, lighter, and much more pliable, leading to planes that are 50 times lighter than at present. Those same improved capabilities will dramatically reduce the cost of travelling into space, making it more accessible to ordinary people and opening up a totally new holiday destination. In terms of technology, the computer industry will be able to shrink computer parts down to minute sizes. We need nanotechnology in order to create a new generation of computers that will work even faster and will have 1,000,000 times more memory, but will be about the size of a sugar cube. Nanotechnology could also revolutionize the way that we generate power. The cost of solar cells will be drastically reduced, so harnessing this energy will be far more economical than at present. But nanotechnology has much wider applications than this and could have an enormous impact on our environment. For instance, tiny airborne nanorobots could be programmed to actually rebuild the ozone layer, which could lessen the impact of global warming on our planet. That's a pretty amazing thought, isn't it? On a more local scale, this new technology could help with the clean-up of environmental disasters, as nanotechnology will allow us to remove oil and other contaminants from the water far more effectively. And if nanotechnology progresses as expected, as a sort of building block set of about 90 atoms, then you could build anything you wanted from the bottom up. In terms of production, this means that you only use what you need, and so there wouldn't be any waste. The notion that you could create anything at all has major implications for our health. It means that we'll eventually be able to replicate anything. This would have a phenomenal effect on our society. In time, it could even lead to the eradication of famine through the introduction of machines that produce food to feed the hungry. But it's in the area of medicine that nanotechnology may have its biggest impact. How we detect disease will change as tiny biosensors are developed to analyse tests in minutes rather than days. There's even speculation nanorobots could be used to slow the aging process, lengthening life expectancy. As you can see, I'm very excited by the implications that could be available to us in the next few decades. Just how long it'll take, I honestly don't know.
That is the end of section 4. You now have half a minute to check your answers.
Recording 66.
You will hear part of a lecture about the history of fireworks in Europe. First, you have some time to look at questions 31 to 40. Now listen carefully and answer questions 31 to 40.
An interesting aspect of fireworks is that their history tells us a lot about the changing roles of scientists and technicians in Europe. Fireworks were introduced from China in the 13th century. Up to the 16th century, they were generally used for military purposes, with rockets and fire tubes being thrown at the enemy. But they were also sometimes a feature of plays and festivals, where their chief purpose was related to religion. By the 17th century, the rulers of Europe had started using fireworks as a way of marking royal occasions. Technicians were employed to stage spectacular shows which displayed aspects of nature, with representations of the sun, snow and rain. These shows were designed for the enjoyment of the nobility and to impress ordinary people. But fireworks also aroused the interest of scientists, who started to think of new uses for them. After seeing one firework display where a model of a dragon was propelled along a rope by rockets, scientists thought that in a similar way humans might be able to achieve flight, a dream of many scientists at the time. Other scientists, such as the chemist Robert Boyle, noticed how in displays one firework might actually light another, and it occurred to him that fireworks might provide an effective way of demonstrating how stars were formed. Scientists at the time often depended on the royal courts for patronage. But there was considerable variation in the relationships between the courts and scientists in different countries. This was reflected in attitudes towards fireworks and the purposes for which they were used. In London, in the middle of the 17th century, there was general distrust of fireworks among scientists. However, later in the century, scientists and technicians started to look at the practical purposes for which fireworks might be employed, such as using rockets to help sailors establish their position at sea. It was a different story in Russia, where the St. Petersburg Academy of Science played a key role in creating fireworks displays for the court. Here, those in power regarded fireworks as being an important element in the education of the masses, and the displays often included a scientific message. Members of the Academy hoped that this might encourage the royal family to keep the Academy open, at a time when many in the government were considering closing it. In Paris, the situation was different again. The Paris Academy of Sciences played no role in staging fireworks displays. Instead, the task fell to members of the Royal Academy of Painting and Sculpture. As in Russia, the work of the technicians who created the fireworks was given little attention. Instead, the fireworks and the spectacle they created were all designed to encourage the public to believe in the supreme authority of the king. However, science was also enormously popular among the French nobility, and fashionable society flocked to demonstrations such as Nicolas Lemery's display representing an erupting volcano. The purpose of scientists was basically to offer entertainment to fashionable society, and academicians delighted in amazing audiences with demonstrations of the universal laws of nature. In the course of the 18th century, the circulation of skills and technical exchange led to further developments. Fireworks specialists from Italy began to travel around Europe, staging displays for many of the European courts. The architect and stage designer Giovanni Servandoni composed grand displays in Paris, featuring colourfully painted temples and triumphal arches. A fireworks display staged by Servandoni would be structured in the same way as an opera, and was even divided into separate acts. Italian fireworks specialists were also invited to perform in London, St. Petersburg, and Moscow. As these specialists circulated around Europe, they sought to exploit the appeal of fireworks for a wider audience, including the growing middle classes. As in the previous century, fireworks provided resources for demonstrating scientific laws and theories, as well as new discoveries, and displays now showed a fascinated public the curious phenomenon of electricity. By the mid-18th century, fireworks were being sold for private consumption. So the history of fireworks shows us the diverse relationships which existed between scientists, technicians, and the rest of society.
Test 2. Exam Practice. Listening, Section 4. You will hear a talk by a meteorologist about weather forecasting. First, you have some time to look at questions 31 to 40.
Pause the recording for 1 minute.
Now listen carefully and answer questions 31 to 40.
I work for the National Weather Service, and as part of your course on weather patterns, I've been asked to talk to you about how we predict the weather. We're so used to switching on our TVs and getting an up-to-date weather forecast at any time of day or night that we probably forget that this level of sophistication has only been achieved in the last few decades, and weather forecasting is actually an ancient art. So I want to start by looking back into history. The earliest weather forecasts appeared in the 1500s in almanacs, which were lists of information produced every year. Their predictions relied heavily on making links between the weather and where the planets were in the sky on certain days. In addition, predictions were often based on information, like if the fourth night after a new moon was clear, good weather was expected to follow. But once basic weather instruments were invented, things slowly started to change. In the mid-15th century, a man called Nicholas Cusa, a German mathematician, designed a hygrometer which told people how much humidity there was in the air. To do this, Cusa put some sheep's wool on a set of scales and then monitored the change in the wool's weight according to the air conditions. A piece of equipment we all know and use is the thermometer. Changes in temperature couldn't really be measured until the Italian Galileo Galilei invented his thermometer in 1593. It wasn't like a modern-day thermometer because it had water inside it instead of mercury. In fact, it wasn't until 1714 that Gabriel Fahrenheit invented the first mercury thermometer. In 1643, another Italian, called Evangelista Torricelli, invented the first barometer, which measured atmospheric pressure. This was another big step forward in more accurate weather predicting. As time went on, during the 17th, 18th and 19th centuries, all these meteorological instruments were improved and developed, and people in different countries began to record measurements relating to their local weather. However, in those days it was very difficult to send records from one part of the world to another, so it wasn't possible for them to share their information until the electric telegraph became more widespread. This meant that weather observations could be sent on a regular basis to and from different countries. By the 1860s, therefore, weather forecasts were becoming more common and accurate because they were based on observations taken at the same time over a wide area. In 1863, France started publishing weather maps each day. This hadn't been done before, and other nations soon followed. So that was the start of national weather forecasting. And I'll now tell you how we at the National Weather Centre get the information we need to produce a forecast. Even today, one of the most important methods we use is observations, which tell us what the weather is doing right now. Observation reports are sent automatically from equipment at a number of weather stations in different parts of the country. They are nearly all based at airports, although a few are in urban centres. The equipment senses temperature, humidity, pressure, and wind speed direction. Meteorologists also rely really heavily on satellites, which send images to our computer screens. What we see on our screens is bright colours. Orange represents dry air, and bright blue shows moisture levels in the atmosphere. The satellites are located 22,000 miles above the surface of the Earth, and it's amazing that despite that distance, it's possible for us to make out an individual cloud and follow it as it moves across the landscape. In addition to collecting data from the ground, we need to know what's happening in the upper levels of the atmosphere. So a couple of times a day, from many sites across the country, we send radio sondes into the air. A radio sonde is a box containing a package of equipment and it hangs from a balloon which is filled with gas. Data is transmitted back to the weather station. Finally, radar. This was first used over 150 years ago and still is. New advances are being made all the time, and it is one method for detecting and monitoring the progress of hurricanes. Crucial information is shown by different colours representing speed and direction. Radar is also used by aircraft, of course. All this information from different sources is put into computer models, which are like massive computer programs. Sometimes they all give us the same story, and sometimes we have to use our own experience to decide which is showing the most accurate forecast, which we then pass on to you. So, I hope next time you watch the weather forecast, you'll think about how we meteorologists spend our time. And maybe I've persuaded some of you to study meteorology in more depth.
That is the end of section 4. You now have half a minute to check your answers.
Pause the recording for 30 seconds.
I